Okay, I want to talk about something. Last class I gave you a lot of questions, but now we're going to talk about only one of those questions, which is operations that can be done on grapes. And I drew a little thing here. We'll talk about it. This is what we're going to talk about today, right now. The numbers thing, we're going to talk about it in the next class, or once the grapes are done. Now, imagine you have 5 grapes with you, okay? And I am gonna write this as 5 at the moment. I'm not going to write it as 1, 2, 3, 4, 5. And one more thing, the reason I want to write stuff down is because typing in English what I'm trying to say, or writing it down, typing, writing, same thing, or speaking it out loud like every single time, it's taxing. I want to have like a shorthand way of communicating. It's the same thing as saying, like, to be honest is TBH, in real life is IRL, and stuff like that. Why do people use it? To make life easy. Right now is RN. So, to make life easy, even in mathematics, we're gonna develop something called a notation. It's called notation. Right now, I have a guy holding grapes so that you understand what, like you physically have a picture running in your head when you see notation somewhere. Now, when I say grapes and stuff like that, see, this is a very naive approach of doing things. And the reason I say naive is because we're innocently talking about grapes, holding them, and we're talking about things that we can count. And another thing is that we are not really writing down a bunch of rules and then building something on the rule. For example, you do geometry. You're going to see that there's a guy called Euclid. And he gave a bunch of rules. He said that there's something called a point, and the point cannot have anything smaller than it inside of it. Like, the point cannot be broken down into smaller parts. Then he said a line is something that is straight, that connects 2 points. And then he said a line does not have any breadth, only has length. He wrote a couple of rules, and then all of geometry came from those couple of rules. Or rather, you take those rules, 4 or 5 things given to you, and you build a whole subject on top of it, not really questioning the rules. Right now, what we're doing, I didn't write any rule. Rules are usually called axioms. I haven't written any axioms. I didn't write anything fundamental. I'm just discussing things. So it's called naive set theory. And this is a real thing. Like, this is actually what mathematicians call it. There's also one more reason why they call it naive set theory, because you don't really talk about the difference between a class, a group, a field, a family, and a set. They feel like they're the same thing, but then they're not really the same thing like, how do I say it? I'll say it some way. It's like the same thing, but not really the same thing. They're all a bunch of things, but those bunch of things have different properties or attributes. Something like that. We'll come to them slowly. I mean, we'll have to come to them at some point in time. We'll come to them slowly. They're gonna be covered while I'm teaching all the things that I am teaching. Not in a full depth, but to some extent I will cover them. So don't worry about that. I will cover them. You will know what they are before you finish this lecture series on set theory. At least you'll know some basics and you'll have some understanding, good enough to read a math book. Yes, and I'll also recommend a couple of books that you can read. Okay. On that note, Paul Halmos wrote a book called The Naive Set Theory. It's pretty nice. It's good for a beginning. But I mean, you can read it right now, or you can read it after seeing these series. That's up to you completely. Let me get back to what I'm trying to say. I am trying to build a notion for you on how to understand things. So we go back to 5 grapes. Now, instead of writing 5 grapes as 1, 2, 3, 4, 5, I'm going to write that as 5, because I have 5 grapes. I know I know, but I want you to understand why. 1, 2, 3, 4, 5, in a sense, is not the number of grapes. 1, 2, 3, 4, 5 is more like, oh, I have 1, 2, 3, 4, 5 grapes. It's like first, second, third, fourth, fifth, if you're counting the grapes. It's like, oh, 1 grape, 2, 3, 4, 5 grapes. It's like you're counting them, but the counting doesn't really represent. Okay, counting represents how many there are, but the counting process, in a sense, doesn't really represent what it is right now. It's 5. It's not 1, 2, 3, 4, 5. When you arrive at the conclusion that you have 5 grapes because you did first, second, third, fourth, fifth, sixth. First, second, third, fourth, fifth. So it's not actually 1, 2, 3, 4, 5. It's more like first, second, third, fourth, and fifth. And first, second, third, fourth, fifth is very different from 5 or 1 or 2 or 3. Like, what is the difference between fifth apple versus 5 apples? Fifth apple is a position. It's not a number. You cannot go to a store and say, give me fifth apple. You can go and say, give me 5 apples. The fifth apple is only the fifth apple in relation to the first apple. So you gotta tell the guy what the first apple is. You gotta choose your first apple. Then you have to tell him the second one, the third one, the fourth, and point him all the way to the fifth one. So you have to do all of this for the guy to give you the fifth apple. You cannot just go and give me the fifth apple. He doesn't know what the fifth apple is until you tell him what the first apple is and in what direction you're counting it, because usually if you go to a store or something, they have apples all paired up on top of each other. So you don't really know where they are. I mean, that guy can count it any way possible. So fifth apple doesn't make sense. Fifth is not a number. I mean, it is a number. It's not the kind of number which is like 5. So that's that. So fifth is basically the first, second, third, fourth, fifth, sixth, all these things. They're basically called ordinals. And they're also obviously numbers. I'll just write it down. They're called ordinals. 5, 4, 1, 2, 3, 4 are called cardinals. It's just fancy names for normal stuff. So, yeah. So 1, 2, 3, 4, 5 makes no sense. Because 1, 2, 3... See, if in this scenario, I want to talk about this again. In this case, writing 5 grapes as 1, 2, 3, 4, 5 doesn't make sense, because 1, 2, 3, 4, 5 means 1 is there, and independently 2 is existing, independently 3 is existing, independently 4, and independently 5. That means 1 grape is there, 2 grapes are there, 3 grapes are there, 4 grapes are there, 5 grapes are there. All of them are there. And then you can say, okay, 1 grape is there. 2 grapes are there, 3 grapes are there, 4 grapes are there, 5 grapes are there. But this is now choosing. You're choosing 1 grape, then you're choosing 2 grapes, you're choosing 3 grapes, you're choosing 4, and then you're choosing 5 grapes. So do you see that 1, 2, 3, 4, 5 doesn't represent the grapes? Because it doesn't make... That's the whole point I'm trying to come to. 1, 2, 3, 4, 5 does not represent the grapes. 5 represents grapes. 1, 2, 3, 4, 5 is you trying to choose 1 grape, and then 2 grapes, and then 3 grapes, and then 4 grapes, and then 5 grapes. Or you understanding that, oh, okay, I can choose a grape. Oh, wait, I can also buy 2 grapes. Oh, wait, I can also take 3 grapes. Oh, my God, I can take 4. Oh, wait, I can take 5. You cannot take 6 grapes from a guy who doesn't have 6 grapes. So I'm not writing 6 over there. So you want to talk about 5 grapes, you want to represent 5 grapes on a piece of paper, you have to write 5. The moment I write 5, I want to say that someone is actually holding 5, or there's some place where all these 5 grapes are at, right? There's a place where all these 5 grapes are at. So I'm considering the fact that these 5 grapes can be at a place. I'm considering there's a person holding these 5 grapes. Eventually, we're just going to remove the person and we're going to see those 5 grapes existing. But right now, we're going to have a person holding grapes every single time we talk about them. So there's a guy holding 5 grapes, almost as if, like this 5, there's a small cushion area here, and that's like the guy holding it. And these are 5 grapes sitting there. And now what I'm going to do, this 5 grapes, now they're obviously from your shop. They have to be from somewhere. So that's where this idea comes from. See, the 5 grapes come from a shop. Apart from that, the 5 grapes after coming from a shop, they are in a place right now. In a room, in your hand. You are in a bigger room. The room's in your house. The house is in the city's in the country. We're on a planet, in a solar system, in a galaxy. You're always a part of something bigger than you. Take it as a philosophical statement of life. You're always a part of something bigger than you, and you cannot evade that process. Now, that's for a group of things you can count. Yes. I mean, we'll come to a couple of ideas eventually. Yeah, where was I? I was at you holding 5 grapes and you're a part of something. So, to represent that you're holding 5 grapes and you're in a room holding 5 grapes and that's it. So I want to represent. So I'm going to have a room every time. I'm going to have a guy holding 5 grapes every time in a room. That's what I'm going to talk about. That's how this whole thing is going to be. Then we're going to remove the guy. In some sense, keep the room, remove the room works. So I'm going to denote the room with these brackets. And now we're going to remove this guy for a moment in our notation. But in your head, imagine there's a guy holding 5 grapes. I want to say that because we're going to come to another situation. So this is basically a set of 5 grapes. That's how you write it down. There's a guy holding 5 grapes. So, okay. Then let's go next. Now you have a bigger room. And the room that you saw over here, this room, that's in a sense we're representing it with the brackets. Okay? We're gonna make sense of things. I am not being very technical because I want people to imagine things. And we're gonna build the imagination in such a sense that the rooms disappear maybe, and maybe the people disappear, and then we can see numbers living in places. We'll go there. Right now we need grapes to go anywhere in our life. Then we have a room. So see, you have to understand you're always living in a room, okay? You're not really existing anywhere. Even if you are in the park, you are in the park. You're somewhere. That place is the room. You cannot just exist somewhere. That is a very important concept. You cannot just exist somewhere and belong nowhere. You belong somewhere. You are a part of something bigger than you. You have to take that into your head. All of mathematics from now on is going to be fundamentally based on that, because set theory is very fundamental. You're going to be a part of something. Every number is a part of something. You got to take that to you got to take it home. It's a take-home policy. So now this is going to be, so this guy is different. This guy is different from this guy. We have all different people, though I know the drawings look the same. Oh wait, they don't actually look that same. So now I'm going to write this as, well, the bracket for the room, and this guy, they're different people, right? With different grapes, so yeah. So now you get it. Okay. Now let us start our thing. So now let's name this room as A. Let's name this room as B. So this set is going to be called A. This set is going to be called B. So what I'm going to do, I shall copy paste this thing. Copy, paste, and my guy, copy, paste, and well, let's talk about them. Okay, let's talk about these guys. So now you have A, you have B. So I'm gonna be like B is equal to 1, 2, 3, 4, and 5. I'm gonna have A is equal to 5. Okay. So now let's talk about stuff. So if I have to, so let's do one thing. Now, here is the thing, right? So the point is, we're gonna have to do something funny here. Rather, it's not really that funny, but what we're gonna do is we're gonna bring this guy. We're gonna see what happens if we put all these guys and this guy in a bigger room. We're like, okay, all you fellas come, and this fella over here, please come into another room. I'm gonna call that room C. But before I do that, I want to tell you something. So you can call him some Rama, some Sita, I guess. Shobana. Okay, I'm giving random names at this point in time. Okay, we're gonna give these people names, but now each of them belong to this room, and belonging is expressed this way. Okay. So 1 belongs to B, right? Because this guy has 1 grape, and the guy, so I want you to imagine 1 as not the grape itself, but the guy holding the grape. And one more thing, so one more other thing. Let us say that all the people who hold the same number of grapes look identical. Okay, that's one more thing. All the people who hold the same number of grapes look identical. Yes, I know this is not a real life scenario, but I want you guys to think that for a moment, like flow with me. So that means this guy holding 5 grapes here, he looks exactly like this guy holding 5 grapes here, in a sense, which means this 5 is not that different from this 5, but they're the same. So they're completely identical, like same person. Like imagine clones of the same person. So all the people who hold the same number of grapes look identical and are identical. Look identical and they are identical. They are identical. So this 5, which belongs to A, or this guy holding 5 grapes, is the same as this guy holding 5 grapes, which again means this 5 belonging to B is the same. So this is the belongs to symbol. Okay, it's like a funny little E. It's the belongs to symbol. So let's do this. So 1 belongs to B, 2 belongs to B, 3 also belongs to B, and similarly 4 belongs to B, 5 belongs to B, 5 belongs to A. Okay. So if something does not belong to, you basically write this and you cut it like that. Like, oh, you don't belong here. So let's see what doesn't belong in A. 1 does not belong to A. 2 does not belong to A. So 3 does not belong to A. 4 does not belong to A. Okay, I should have written that better. I'm probably stacking everything up in the same place. I'll not do that, okay, from now on. So what I'm trying to get at here is first the belongs to symbol, then does not belong to symbol, then I'm naming sets as A and B, And I told you this. All the people who hold the same number of grapes look identical. They are identical. Okay. So now what I want to do is I want to have a room which has all the people of B and all the people of A in one room. And I'll also have another rule. No room can have two identical people. Or something like clones not allowed. So every person comes only once. Okay. And if you look identical, we're just going to take one of you guys. So if you look at it, so I want all the people in room number B and room A in room C. So I'm going to have a room over here. It's going to be called room C. So I'm going to put this guy with the 1 grape. I'm going to put the guy with the 2 grapes. I'm going to put the guy with the 3 grapes. Also, person with the 4 grapes. Okay, I think I need a bigger room. We'll have a bigger room, no problem. I'm gonna put the person with the 5 grapes. That's all the people I've covered from room B. But remember, there's also another guy with 5 grapes in room A, so we're gonna have them over here too. Okay, but again, as we have decided that all the people who hold the same number of grapes have to be identical, from this policy that we have invented all by ourselves, not giving a thought about the world. We didn't care about other people. We just came up with the policy and we're like, no. So from this policy here, these guys are the same. You know, they're like identical. They're like clones. And we have another policy. Every person comes only once. You cannot have 2 people looking exactly the same. So it's funny. So we did 2 funny things. This is more realistic. You cannot have exactly identical people in the world. But this thing is not realistic. Of course I can hold 5 grapes and my sister can hold 5 grapes. But I'm not letting that happen. So I did something funny. I said, I can hold 5 grapes. If you hold 5 grapes, then you have to be my clone. And then I said, in a room, 2 clones cannot be there. Only one person of that clone can be there. So, I get it. I know it's a bit twisted, but hey, that's what we want to do right now. Why do you want to do all of this? Probably because it's fun doing stupid things. I mean, think about it. This obviously sounds very stupid to do. No harm against all the mathematicians. I love doing this, but from a perspective of somebody else who doesn't do this every day, he would say, why do you want to make people identical? Then if you want to do that, you want to clone people all over the place just because they're holding the same number of grapes, why on earth won't you let them live in a room together? I mean, why would you not? So why would you make as many, now think about it as numbers for 1 second. Why would you make clones of 1 everywhere? And why would you not let all those 1s live in a room? Why would you not give them a seat? Now you're like, oh no, only 1 is allowed to be here. Only 5 is allowed to be here. 3 is allowed to be here. If I have to say something like the set of natural numbers, now I'm just saying stuff for the people who probably know it. Why do you only allow 5 to exist in the natural number set? Why not 2 of them, 3 of them? But again, you happily do 5 plus 5. You clone 5 2 times, add 5 to itself, make 10, but you won't let the clone exist in the set. You're not letting that happen. But yeah, so I don't want to talk about that right now. I mean, it's the same thing essentially, but from an outside perspective, if you think about it as human beings, because I want you guys to think, I want to give you guys the real, like the perspective where numbers are real, they're alive. But before saying all that, I want to first show it in terms of human beings. Once you're used to that, then I want to show you what we're actually doing with numbers and how ridiculous it feels like if you think numbers are alive and you actually see us doing math. It feels crazy. So I want you to have that vibe. That's why I'm doing this. I don't mean math is stupid. No. Math is fun. But it's just stupid sometimes. Not like it's dumb. I guess I'm just freaked out about people who are going to have opinions about me because I said this. Math is amazing because it's fun. But at the same time, it's ridiculous in terms of real life. It's stupid, ridiculous, not in a bad way, but in like the most bizarre way possible. And that bizarreness about it makes it fun. Yes, it's ridiculous. Okay. Yeah, so this crazy little thing that we said here. So yeah, I said I'm gonna make clones of people, then I won't let the clone be there. Right, great. Crazy, actually, but let's see what happens. And what I was actually trying to say is that you don't have to, I mean, this is just how math is gonna be most of the time. We're gonna do crazy stuff and funny stuff, ridiculous stuff, and have fun doing and imagining all these ridiculous little things. That's what most of this is going to be about. So just have fun at this. We literally allowed clones to exist. Don't take it too seriously, guys. Like, let's just have fun. We allowed clones to exist, then we don't give them a room or a house. So let me not repeat myself. I'll just go forward. So we are still in the making of the room C. It's still in the making. And now this every person only comes once thing, this rule we have over here, we have to eliminate one of these guys, but they look identical, so whoever we eliminate doesn't really matter. It's the same thing. So I choose to eliminate this guy, same guy. Elimination. So I shall erase him. There you go. Okay, but this literally looks like room B at this point in time, if you don't really mind the shape of the room. So now let's say one more thing. The room is identical if it has the same elements. Oh, wait, I said something interesting. Elements. Yes, these guys, the same. Okay, these guys, the human beings, they're called elements now. Okay. The rooms are same if actually it's if and only if, but fine. If and only if they have the same elements, the same people. So the if and only if comes like this. It's basically saying that these are like two parts, actually. So one part basically says that there are two things you do here. Okay, so you look at room number B and you see that, oh, okay, first guy, are you there in C? You're there. Second guy, are you there in C? You're there. Third guy, you're there. Fourth guy, you're there. Fifth guy, you're there. The second part of the statement, the only if part of the statement, you look at room number C, you're like, are you there in B? Yes, you're there. Are you there in C? Are you there in B? You're there. This guy? Yeah, you're there. That guy? You're there. This guy? You're there. So you might ask me, why do you need this ridiculous two-step verification? Like, why? Simply because, take this. Let's go back to A and B. Let's see that is A equal to B. If I only do one-step verification, I would say, A, this guy, are you there in B? Yeah, you're there in B. But then I'd be like, A is equal to B because I said if elements of A are in elements of B. But I didn't talk about the portion where elements of B also have to be in A. The people in B also have to be literally in that other room. Like, I get it that you have a clone with 5 grapes there, and you have a similar clone of 5 grapes in this room. But what about the guys with the 4 grapes, the 2 grapes, the 3, and the 1? What about these guys, man? Like, come on, let them have a life. What about them? They're not there in that room. Why would the 2 rooms be the same? So if you only do like one-step verification, then yes, you would come at bizarre conclusions like room A is the same as room B. So you got your two-step verification. Let's do that. That's this. Are you there? You're not there. Are you there in A? You're not there. Oh, you're not there. You're not there. You're there though, but it doesn't matter because even if one person is not there, it doesn't really matter. All of them have to be there. So all the people in one room have to be in the other room, and all the people of that room have to be in this room. And that's when you say that they're equal. So now let's write stuff down. So B is equal to C. Okay, cool. Another thing. So let's also see okay, so what's going on between A and B? Because you have a person here, the clone with 5 grapes, the same guy, the clone of this dude is also here, but also other people are there, so it has more number of people. So we have to do something about it. So how do you write that B has more number of people while B also has the elements of A? So now I'm going to use the word elements. A person is now called an element. A person holding a grape is basically called an element right now, okay? So yeah. So let's look at that. So what do you do if 1, 2, 3, 4, 5? Yes, so A, that guy, his clone is there in the room B, but room B has more people. So how you write that? So there's 2 things, okay? B has more number of people. Okay, we're not talking about just the number of people. We're talking that B has more number of people, but B also has all the people that are there in room A. So there's another thing I'm saying here. Room B has more number of people. Okay, NO dot is just like a simple way of writing number. I mean, a lot of people do that, so I did it. Room B has more number. Whenever I do NO dot, it's just number. More number of people than A. Okay. And what's happening is room B has all the people that room A has. How do you represent that? You represent that by saying B, okay, is a superset of A. So I'm gonna also tell you what there's also one more way of writing it. Actually, this is how you write it. I'll tell you what that is. So this is called B is a superset. Oh, it's super. I'm not even making this up. You guys have to take the word this way or they won't make sense. You're super. It's a superset. I'm not even kidding. So B is like the superset of A. And A is the subset. Like the suburban area. No, sub is usually used for denoting small. Super is usually like you're bigger, you're wow, great, stuff like that. So B is the superset of A is the subset of B. Yeah, math is very dramatic. Actually, it is. Okay, so now what about the funny little line I wrote here? This is basically to say they're equal. So this line actually talks about equality. So to say, if you want to clearly say that B has more number of people than A, then you basically write this and then you do that. In a general case, if you want to say B has all the elements, that A has, then you write simply B is superset of A, which basically means that, well, there are two options, right? One, B, number of elements in B is basically more than number of elements in room A. I mean, it's written like this, actually, literally. Or number of elements in room B is equal to number of elements in room A, because if they were equal, then obviously all the elements in A would be in B, all the elements in B would also be present or available in A. Like all the people that I can find in room C that we saw before, I would also find them in the room B. And all the people I found here. So we're just trying to write that here, that's what we're trying to do. We're just trying to write that the room B has all the elements that are there in room C. So that is this. And the room C also has all the elements that are there in room B. That is this. So when C is a subset of B and B is a subset of C, you basically write B is equal to C. So usually if you want to say something is equal to something, you first start proving that this is a subset of that and that's a subset of this, and then you arrive at the voila, they're equal. That's how you do things. So what does C being a subset of B mean, or B being a superset? You basically start with C. I mean, you can start with C, and then you can be like, oh, are you there? You're there. This guy, you're there. That guy, you're there. This guy, you're there. And B being a subset of C means you start with B. Oh, you're there. Oh, you're there. You see a difference in directionality? If I want to check C is a subset of B, I'm going to start looking in C, and then I'm going to, shift my head to the room B. But if I want to check whether B is a subset of C, I'm going to start with the room B, and then I'm going to check into the room C. So there's a little directionality difference. I want you guys to understand that. The reason we write this little line over here is to say that there is a possibility, as we know right here, that if there are all the people in, so yes, this is what I was saying. If all the people in the room B are also there in the room C, there are only two possibilities, right? The number of people in room C either are, first of all, I want to say this. So you have this guy, this guy, this guy, this guy. So one is the number of elements in room C, number of human beings in room B, they're the same. That's one option, obvious option. That's one option, which is represented by this line over here. The other obvious option is they're greater. For example, if there was, let's say, ridiculously, room number C had a person who basically... So I was trying to say that so one option was equality, the other option was greater than. So if there was randomly a guy with, let's say, 6 grapes, then what would happen is, still you can say that, oh, if you go to B and if you check, you still have all the people you see in the room B, you still see them in room C, but room C will have an extra guy. So room C will not be a subset of room B, but room B will be a subset of room C. Then you can say NC is greater than NB. That's when this portion makes sense. So that's what this is about. The equality is basically for when they're equal. This other portion is for when it's not the case. So when you write it this way, when you say that room B clearly has more elements than room A, or room B clearly has less people than room C, and when you clearly write it this way, okay, then it's called a proper set. It's called a proper set. So that's some terminology, right? That's a lot of terminology that we're trying to think and talk about. So I want you guys to think about this. It's a short video. We're doing a couple of things. I first want you guys to get a hold of these couple of rules. Even writing them down is fine. Okay, like write them down, like seriously. I want you guys to remember these notations. This is belongs to. Okay, this is does not belong to. That's one more thing, you know. Then I want you guys to like make a 5-10 minute notes on everything I've written down. Like not notes, but you know, you're understanding. Like draw a room, put people there, represent, and write the subsets and stuff like that. So I'll just write it down like this. So A is equal to 5. B is equal to 1, 2, 3, 4, and 5. So you have A is a proper subset of B. And this is, if you just see, it's literally the same thing, okay? It's the same thing. I just reverse wrote it, and they're the same thing. This is the subset notation. This is the proper subset notation. This is the proper superset notation. It's like this is subset. This is proper subset. This is superset. This is proper superset. So when the left hand side and then the right hand side. The left hand side is the subset of this. That's how this works, okay? Another thing is elements. So 1, 2, 3, 4, 5 are elements for B. 5 is elements of A. So we wrote 5 is equal to belongs to A. And 1, 2, 3, all this belongs to B. So I want you guys to come up with a couple of ideas for people holding different number of grapes. I want you to do that. Now, why I put comma here is they're different people. A guy was holding 1 grape, another guy was holding 2 grapes, another guy was holding 3 grapes, another guy was holding 4 grapes, you know? Because of the thing we said that if you're holding different number of grapes, you're different. They're all different. You cannot just mumbo jumbo everything and be like 1 plus 2 plus 3, 6, plus 4, 10, plus 5, it's just equal to a guy holding 15 grapes. You cannot do stuff like that. They're different, bro. They're like different number of people in a room. 5 different people holding different number of grapes. This is seriously not equal to a guy holding 15 grapes. No. The number of grapes in B, if you call this D, you know, this thing, if you call it D, the number of grapes, ideally you should write it this way. You should ideally write it like this. So, number of elements in B might be, it is the number of elements in D, but B is not equal to D. I get it. Oh no, what the hell am I saying? Sorry. Number of elements are not equal. What am I saying? I'm sorry. This has 5 elements. This has 1 person. That has 5 people. No, they're not equal. Number of elements of B are not equal to number of elements of D, and they're not the same. So all of this doesn't really matter. Even if you look at these 2 sets, it's just 1 guy holding 5 grapes and 1 guy holding 15 grapes. Number of elements of A can be number of elements of D. No, 1 person kind of a thing. But A is not equal to D. Like, this guy is holding 5 grapes. He's a different person from the guy holding 15 grapes. People who hold different grapes are different. They're distinct. All the people who hold the same number of grapes look identical. And I'll add one more line over here. All the people holding different number of grapes are distinct. Holding different number of grapes are distinct. That means they're different. And different. Sorry, should just are different. Different. Okay? So, yeah, they're different, okay? They're very seriously different. If you want, like, pause it and take a Photoshop of, like, a screenshot of this and then in your own words write it down. But this is important. You need to know. They're very, very different. So we have introduced a couple of symbols, a couple of things. So the number of elements or number of people in a set is called the cardinality. The cardinality of a set. So this is it. This is where I'm gonna end the class. So the next class I'll still have to talk about sets, but I want you guys to write brief notes on this, think about it, and then we'll look at what other things we can do with people in a bunch of rooms and what other silly little rules we're gonna keep, like cloning and stuff like that, and we're gonna understand the subject that way. And the room size is going to get bigger and bigger and bigger, and that's going to be probably the best part of this theory or this subject in itself, because the room size is going to get so big, it's going to be hard to count it. That's the whole point. So the room size right now, let's say the room size or the cardinality is the number of people in the room. Let's say it that way, because every person occupies, let's say, some like 20 by 20, 400 feet square. So if you have 5 people, then they'll occupy like 400 into 5. What is it? 2,000 square feet. So let us basically say, have some kind of proportionality that, okay, number of people in a room is the size of the room. We're gonna have rooms, if as we keep going, we can imagine rooms with crazy amount of people that it's hard to count them. It is, actually, it's hard to count them. So, okay. So that is basically it. Then at some point of time we are going to have to jump from our idea of people holding grapes. It's gonna get complicated. I mean, it's gonna be a lot to imagine in the head with people holding grapes, but we're gonna have to get over that and go to we're gonna have to get over that and probably start writing numbers themselves instead of grapes and people, but we're gonna do this grape people thing for a while. We're gonna also take the whole story into something called natural numbers, integers, rational numbers. Then we're gonna get into irrational numbers. Then we are going to see what the hell's actually happening with irrational numbers and rational numbers and where they are, where do all these numbers live and stuff like this guy lives in the room. The guy holding 5 grapes, he lives in the room. But the funny thing is, one clone is living in the set called A, or the room A. The other clone lives in the room B. So is there like a fundamental place from where these clones were made from? Was there like a warehouse or something where you have like one guy in that room and all the clones come from this guy? Is there a room like that? We're gonna find these rooms, where these numbers come from. And then we're gonna try to see it in real life, like literally in front of you, anywhere you are, you will be able to see these numbers in front of you. That's the whole idea. They're all there in any straight line you can draw, even on curved lines, but they're there everywhere. So we're good. That's the whole idea, to be able to see. Then we're gonna start counting. Then we're gonna look at gaps. We're gonna see if we can fill in the gaps. Something like, roads in India have a lot of holes in it. We just want to fill all the holes in so we can have a smooth road to walk on top of. That's one thing we're gonna do. Once we finish the gaps and the holes and the road is smooth, then we're gonna do other things. Then we're gonna jump from one road to the other road and stuff like that. Then we're gonna call people traveling on different roads, and We're going to jump to those roads. That's what we're going to do. Actually, that is what we're going to do. And that jump of one road to the other road, or one room to the other room, it's going to be called a function or relation, and the jumping itself is going to be called a relation or a function and stuff like that. You're going to jump from one room to the other room. Right now we're going to do set stuff. Right now it's sets. Once we're done with sets and we have natural numbers, integers, rationals, irrationals, then we have real numbers. Then we're going to start doing things with these, adding them, subtracting them, multiplying them, stuff like that. Then we're going to jump from one room to the other room and see how all that looks like. So that's functions, relations, and stuff like that. Then we're going to see in how many times we can jump, and then we're then going to go into like the heart of calculus. Which is something a bit like, imagine, now you're going to have to imagine a road at this point in time. You have a road. You're going to jump from this road to that road. The road you're jumping on top of, is that road is that road smooth? Does that road have no holes? Is basically the topic of continuity. Can you literally run a car on the road is differentiability. So if the road doesn't have holes, but if the road ends at some point, at that end point, how do you run a car? You can just stand at the end point, but you can't start your engine and run, because at the end point you can't go anywhere, because there's no road after that point. Let's say there are no holes, but if there's no road after a particular point, how do you run your car? You can't. So some stuff like that. So whether can you run the car on a road? Literally, I'm not kidding. That's what we're gonna do. Can you start your engine? Not. Differentiability. And if you do start your engine, how fast can you go on this new road of yours? Differentiation. If you have traveled whatever you have traveled, how much did you travel? How much time did you take? How much distance did you cover? Some stuff like that. Then you get into idea of integration and stuff like that. That's pretty much mostly it. Then you have differential equations, which is in a way an equation in itself, which has the speed of this car, to say, basically, in a sense. So that's what we're gonna actually be doing. And we're going to write it down like equations every single time. And try to imagine the real case scenario of it. Well, that's not most of it. So this topic of sets is going to end up going into calculus. Yes, it's the beginning. It's not just the beginning of calculus. Sets are the beginning of everything, because there was a funny little dispute that goes on in mathematics or for mathematicians. I hope it's resolved by now. I think it is, mostly. What is more fundamental as a building block? Is it a bunch of grapes, or is it a room with grapes? So that was the question. Are rooms with people holding grapes a fundamental building block in building mathematics? Or a person holding grapes without really talking about the room, is that more fundamental? So the dispute was, is 5 a better beginning? 1, 2, 3, 4, 5 numbers, are they better as fundamental blocks of mathematics? Or something like 1 and 2, or 2, 3, are sets more fundamental building blocks of mathematics? That is one funny, interesting, this is not really funny, this is just interesting. When I say funny, I don't mean to say that it's stupid or like not in a ridiculing sense that that's so stupid, oh so funny, oh so mediocre. I don't mean that. I mean like, okay, if you see anime, I mean like, omoshiroi desu ne. Like, oh, it's so interesting. Oh, it's so fancy. Oh, wow. Kind of a funny, like something that sparks your mind, kind of a funny thing. That's what that's what I mean when I say funny. So this is gonna be it for today. And then maybe the next day we can go for continue our discussion further for sets. As far as the syllabus is considered, you don't really have a lot, so we're already halfway there for sets. Another halfway is intersections and unions and difference and symmetric difference and complements and stuff. That's literally the next class. In a way, sets are done for the syllabus. Then we can get into Cartesian products, relations, and functions. I'm just naming stuff at this point in time. So yeah, once that is also done, we can and once sets in a way are done, like I will try to give some example questions to solve, maybe in the video itself. So I don't think it should be that difficult, but you will have to put pen on paper and think about stuff and draw them and put rooms and get used to this notation, the funny little e, striking it and being, oh, that doesn't belong to, e is belongs to. It's not really called e, by the way. So yeah. Okay.